Welcome to the 12th lecture of my series on thermodynamics. In the last lecture, we met the very important concept of reversibility, and we defined a process to be reversible if, after it has been carried out, it is possible to return both the system and the surroundings to their respective initial states, that is, states they were in before the process had been carried out. And this has to be done without any other effect. Now we did see that almost all natural processes are actually irreversible. Some examples that we looked at were complete conversion of work into heat, cannot be reversed. Transfer of heat from a higher temperature to a lower temperature, which happens spontaneously, again is something which cannot be reversed. And so on. We also saw that all these irreversibilities were really not different phenomena, or they were different phenomena, but they did not really require an entirely different set of explanations. They could all be explained away if you assume as a basic fact that one of these phenomena is actually irreversible. And basically, what all of these experiences sum together as is what is called the second law of thermodynamics. That is what we are going to describe today. However, before we go there, what we need to talk about is an old friend, the Carnot cycle, and we had already mentioned this at that time, although it was just mentioned because it was still ahead of the logical flow at that time, that the Carnot cycle happens to be so important primarily because it is the simplest possible reversible engine. The Carnot cycle, remember, is composed of an isotherm followed by an adiabat, then an isotherm and another adiabat. All of these steps are quasi-static and dissipation free. So, of course, all of these steps that are being carried out are actually reversible. This is something we have already seen in the last lecture, that in order to be reversible, a process has to be quasi-static and dissipation free. What is extremely important is that the Carnot cycle is the only possible reversible cycle which uses only two reservoirs. No other process can be carried out with only two reservoirs in a reversible manner. Now, why is that the case? Note that for a cycle to occur, there must be places where the system accepts heat from a reservoir, also other situations where it might reject heat to a reservoir. But whenever heat is exchanged with a reservoir, if it is to be reversibly done, it cannot happen at a finite temperature difference. As we mentioned a while ago, heat flow which occurs from a hotter body to a colder body, whenever there is a finite temperature difference, must be irreversible. So, the only way in which the heat exchange is feasible in this case is that the temperature of the system and that of the reservoir must differ by an infinitesimal amount. When the system is accepting heat from the reservoir, its temperature must be infinitesimally lower than that of the reservoir. And when it is releasing heat to a reservoir, on the other hand, its temperature must be infinitesimally higher. But it is an infinitesimal difference under which heat exchange is possible, otherwise you cannot have a reversible change. Therefore, the only possible heat exchanges which occur if you are insisting on a reversible cycle with two reservoirs must occur at the temperatures of the two reservoirs, that is, isothermally. Now, of course, in order to complete the cycle, the system must somehow go from the temperature of one of the reservoirs to the temperature of the other reservoir. Now, there may be many different means of changing the temperature of a system, but if it is to exchange heat with any object in between, and note that the only objects you have are the two reservoirs, then again the heat flow would be irreversible. So the only way in which you could reversibly complete the cycle while going from one temperature to another as the need arises is to change the temperature adiabatically. Of course, any adiabatic step will not do. You will need to carry out a quasi-static dissipation-free adiabatic process. But if you do that, that exactly gives rise to the Carnot cycle. The only places where heat is exchanged is in isothermal expansion or isothermal compression, and the other parts has to be carried out adiabatically. This isothermal adiabatic cycle is the only possible cycle. So when we are dealing with two reservoirs and two reservoirs alone, then the words Carnot cycle and reversible cycle essentially mean the same thing. Of course, irreversible cycles which occur between two reservoirs are different from Carnot cycles. The special feature about Carnot cycle that we had seen earlier, that no matter whether we use an ideal gas with a variable heat capacity as a working substance or even a van der Waals gas as a working substance, we end up with exactly the same calculated efficiency. That, of course, was not an accident. The Carnot cycle happens to be the only possible reversible cycle running between the same two reservoirs, and we will see later that Carnot's theorem guarantees that all reversible cycles running between the same two reservoirs, irrespective of what the substance etc. are, must give you the same efficiency. What makes this particular result very important from a theoretical point of view is simply the fact that this guarantees that there are engines which can be run in reverse. The Carnot engine, as you can see on the left here, is one which takes an amount of heat Q1, a positive amount of heat Q1, from a reservoir at temperature T1 or θ1, depending on whichever scale you are using to talk about temperature, takes in a negative amount of heat from another reservoir at temperature T2. This is the one where the heat is actually being rejected, and does some amount of work which is positive. You can run this engine in reverse and automatically end up with a W. The W corresponding to Carnot refrigerator now, which is negative, and Q1 and Q2 are still the heats flowing in from reservoirs 1 and 2 into the working substance here. But this Q1, of course, is negative of that Q1. This Q2 here is negative of that Q2. The all-important thing is, you can run this particular thing either in the forward direction or in the reverse direction. This is actually going to play a very important role in the discussions that we are going to enter into right after we finish talking about the basic form of the second law of thermodynamics. In fact, the basic form in which we are going to state the second law of thermodynamics is something that we have already mentioned several times in previous lectures. But let me just formally introduce them to you this time. There are several different versions of the second law of thermodynamics, and you are going to meet many such versions in subsequent lectures. For the time being, let me talk about two statements which are very, very common. These are equivalent statements, so they are not really two different laws, but they are not obviously equivalent, so we have to check why we are calling them the same law. The first statement is the so-called Kelvin-Planck statement, and that involves an engine which played a central role in our discussion of irreversibilities earlier. A process that undergoes a cycle while absorbing a positive amount of heat Q from a single reservoir, this reservoir here, and converts it entirely into work W, which is of course the same as Q and hence positive, is impossible. Note that this is essentially the same thing that we have talked about earlier when we said that 100% conversion of work into heat, which is very possible, is an irreversible process. This statement simply mentions that in a formal way. It's named after two very famous phrases. Lord Kelvin and Max Planck. Kelvin was the person who actually stated the law in this form first, although his version was slightly more complicated in its statement and also mentioned things like it is impossible by the means of any inanimate agency to do certain things. Now, the reason why inanimate agency had to be mentioned by Kelvin was that at his time people were not very clear whether living beings, animate objects, are also governed by the same laws of physics as the rest of the world is. Today we know that the laws of physics work equally well for living objects as well, and so we make no reference to whether it's an animate object or an inanimate object in discussing the Kelvin-Planck statement. The statement in this particular form essentially is due to Max Planck. Now, the pictorial depiction we have here is actually not of the statement itself, but rather of an engine which, if it had existed and of course had also had a positive amount of work, then this would have violated the Kelvin-Planck statement. That is why we have denoted this engine pictorially by this, something which draws heat from one reservoir and converts it entirely into work, and its name that has been given here is Kp bar. This is the anti-Kelvin-Planck engine. An engine like this, had it existed, would have violated the second law of thermodynamics, at least the Kelvin-Planck statement of the second law of thermodynamics. Now, another very closely related version of the second law of thermodynamics that is very often used and actually happens to be something we have already met before is a so-called Clausius statement. In the Clausius statement, what we say is the following: a system that undergoes a cycle that transfers heat Q2, which is positive, from a reservoir at a temperature T2 smaller than T1 to a reservoir at a higher temperature T1, of course, without any other effects. So delta U is 0, W is 0, so Q1 and Q2 have to be negatives of each other. Now, such an engine is impossible. This is nothing but saying that the spontaneous flow of heat from a higher temperature to a lower temperature without any other effect is irreversible. You cannot do that in reverse. So any engine like this would have actually been able to reverse that. And that is exactly what the Clausius statement of the second law says cannot happen. So both of these statements of the second law that we are meeting here are things we have already seen before as statements about phenomena which are irreversible. But when you want to explain why phenomena are irreversible, you have to start somewhere. You have to either assume that 100% conversion of work into heat without any other effect is irreversible. That essentially is the Kelvin-Planck statement of the second law of thermodynamics. Or you have to assume that the flow of heat from a hotter body to a colder body without any other effect is irreversible. And that exactly is what Clausius statement is. But as we have kept on insisting before, these two statements are not two different laws. They are both the second law of thermodynamics. And the reason behind that is that these two statements are equivalent. Equivalent here means that one statement implies the other. That is, Kelvin-Planck statement implies the Clausius statement, and the Clausius statement implies the Kelvin-Planck statement. It has to work both ways for the statements to be equivalent. On the other hand, both of these statements are really negative statements. Statements that the anti-Kelvin-Planck engine, one which converts heat into work 100% without any other effect, is impossible. Or that the Clausius engine, anti-Clausius engine, something which would take heat from a cold body and move it to a hot body without any other effect, that is impossible. Now, negative statements are actually difficult to work with. But the opposite of the statements as they stand are actually positive statements. In other words, the negation of the Kelvin-Planck statement would simply mean that an anti-Kelvin-Planck engine exists. A negation of the Clausius statement would simply mean that an anti-Clausius engine exists. So, the equivalence of the two statements can also be read in this exactly equivalent fashion. Anti-Kelvin-Planck implies anti-Clausius, and anti-Clausius implies anti-Kelvin-Planck. In other words, if by some means I had gotten my hands onto an anti-Kelvin-Planck engine, I can use it and other things which do exist to produce an anti-Clausius engine. On the other hand, if somebody had given me an anti-Clausius engine, I could use that along with other things which do exist to form an anti-Kelvin-Planck engine. Existence of one kind of engine immediately implies the existence of the other kind. So if one of the statements is violated, so is the other one, and vice versa. That is the same thing as saying if one of them hold, the other one also has to. So let us now try to see exactly where this equivalence comes from. And this in fact is where the fact that we do have two reservoir one heat source engines which are reversible, that is Carnot cycles, comes in very, very handy. So first let us prove that the negation of the Kelvin-Planck statement implies the negation of the Clausius statement as well. Kp bar implies Cl bar. In other words, if I have an anti-Kelvin-Planck engine, something which can take a positive amount of heat Q from a reservoir at temperature T1 and use it entirely to produce work while going in a cycle, of course the work has to be equal to Q in this case. If you did have such an engine, then using that you can actually produce an anti-Clausius engine as well. Now the tool that we will need for this is another engine which we know exists, the Carnot engine, which we are assuming runs between two reservoirs. One of them is the same reservoir as the one which our anti-Kelvin-Planck engine uses, the reservoir at temperature T1. I've shown them as two different bodies in this picture simply for clarity, but they are basically the same reservoir. And what it does, it takes Q1 prime amount of heat from T1, Q2 prime amount of heat from T2, which means it actually rejects minus Q2 prime amount of heat to T2, and does an amount of work W prime, which is of course the sum of Q1 prime and Q2 prime. Now what is important here is that by choosing the scale of the system appropriately, by either changing, say, the amount of the gas in my Carnot cycle, if I'm using an ideal gas Carnot cycle for example, and or increasing the expansion ratio, I can adjust the W prime until it becomes exactly equal to W. So whatever amount of work the anti-Kelvin-Planck engine does, I have managed to find a Carnot engine, an engine which really exists, at least in its ideal form, it does exist, which does exactly the same amount of work as this engine. Now what is very important is that the Carnot cycle can be run in reverse, and that's exactly what we are going to do next. If we run the Carnot cycle in reverse, note that in this picture this one and this one are exactly the same thing. I've just decided to run this one in reverse. So what it does is now takes minus Q1 prime amount of heat from T1, which of course means that it's actually rejecting heat to T1, takes minus Q2 prime amount of heat, which is now positive from T2, and of course, as a result of all this, does minus W prime amount of work. Whatever work the engine did, the reverse version does exactly the negative of that. Note that this is possible only because the Carnot engine is reversible. And now minus W prime, of course, has to be equal to minus W. Then what we will do is simply this. We are going to consider this one which has gone round in a cycle and this one which has also gone round in a cycle. The arrow is reversed just to show that it's running in reverse now. But both of them have gone round in a cycle. We can take them both together as my working substance, because ultimately the one important feature of an engine is that the working substance has to go back to the same state it started out with. So that is perfectly possible if we take both this substance and this substance together and consider them together as my engine, which I have tried to indicate by this dashed dotted green line here. So whatever is inside this light green line is actually my engine. Whatever is outside are, of course, external reservoirs or things they do work onto and so on. Note that when you take these two things together, the two works, W and minus W prime, which is minus W, together cancel each other out. So no external work is being done either by this engine or no work is being done on this engine. But what does this engine do? It actually takes minus Q2 prime amount of heat from T2 and takes Q minus Q1 prime amount of heat from T1. Does no work, goes in a cycle. So it's obvious to see that the minus Q2 prime heat here and Q minus Q1 prime amount of heat here must be negatives of each other. And you can easily check by using the fact that W prime is actually Q1 prime plus Q2 prime, that actually is true. Indeed, you didn't have now to check that. First law of thermodynamics would of course ensure that the net heat taken in by this engine has to be zero, there being no delta U and no W. But let's see what has happened as the upshot of all this. This engine, the bigger one, inside this green line, does no net work, or nothing from the outside does net work on it. It takes a positive amount of heat from T2, minus Q2 prime is positive, and rejects the same amount to T1. In other words, what we have made by combining them together is nothing but an anti-Clausius engine, something which does no work but takes heat from a colder reservoir and gives it to a hotter reservoir. So, the existence of an anti-Kelvin-Planck engine would immediately imply the existence of an anti-Clausius engine. All you need to do is put that in connection with a Carnot cycle running in reverse, and you're done. So the part where the failure or the negation of the Kelvin-Planck statement implies the negation of the Clausius statement has been proven. In order to show equivalence, we have to show that the implication works the other way around as well. And to do that, what we need to do is start with a scenario where Clausius statement has been violated. So we have an anti-Clausius engine, an engine which runs between two reservoirs at temperatures T1 and T2, takes Q1 amount of heat from T1 and Q2 amount of heat from T2 without any work being done. Of course, that means Q1 and Q2 are negatives of each other. What makes this an anti-Clausius engine is Q2 is positive. Note that here T1 is more than T2, so the heat is flowing from the colder reservoir to the hotter reservoir without any other effect. You do have an engine in between, but the engine's material is back to the same state. There is no work being done, so everything else is also in the same state. Now, in addition to this, what we also have is another reversible engine running between the same two reservoirs at temperatures T1 and T2. Well, taking heat Q1 prime and Q2 prime from T1 and T2 and doing W prime equal to Q1 prime plus Q2 prime amount of work. Note that I can adjust Q2 prime, or rather adjust the scale of the cycle, this Carnot engine, in such a way that Q2 prime obeys this equation. Q2 prime is negative of this Q2. Remember, in our anti-Clausius engine, Q2 was positive. So negative Q2 is negative, which is what Q2 prime is. So it's possible to adjust the scale to keep Q2 prime at any negative value I want, including minus Q2. Now notice that as a result of all of this happening, what has happened to this reservoir at temperature T2? Once again, let me remind you that this and this are the same reservoirs. They have just been shown as separate simply for ease of drawing. So are this and this. So one reservoir at temperature T1 here, another reservoir at temperature T2 here. Now, if you focus on the second reservoir, the reservoir at temperature T2, you would notice that the net amount of heat it gives to the system is Q2 plus Q2 prime. And that is simply equal to 0. In other words, the reservoir at temperature T2 gains through the Carnot engine whatever energy it lost to this anti-Clausius engine. And therefore, once one complete cycle of each has completed, this is back to its original state, this is back to its original state, so is the reservoir at temperature T2. And therefore, you can put all of them together, this engine, and this reservoir, because remember, now that it's back at its original state, it can be thought of as part of the working substance of an engine. Let me remind you once again that a reservoir is labeled by basically its temperature, but its state is essentially determined by how much energy it has. So as long as the reservoir loses and regains the same amount of energy, its state will not change as a result of the whole thing. So what you now have is another super engine enclosed by a dashed green line. Our original anti-Clausius engine's working substance, the Carnot cycle's working substance, and the reservoir. All three are inside, and all three can be put inside because each and every one of them are back at their original state. But what is this overall thing doing? Notice that this, of course, has zero work, but this had a positive amount of work W prime before. If we put them together, this is something which interacts with a single reservoir, the reservoir at temperature T1, and does a positive amount of work. Of course, the amount of heat it takes from the reservoir at temperature T1 is Q1 prime minus Q2, and you should be able to do a calculation, not a very difficult calculation, to show that that amount is exactly equal to W prime, but that essentially is guaranteed by the first law. What it does do ultimately is this. It takes away an amount of heat from the reservoir temperature T1 and converts it entirely into work. And that is exactly what we mean by an anti-Kelvin-Planck engine. Something which goes in a cycle, takes in a positive amount of heat from one reservoir and converts it entirely into work. In other words, if you have an anti-Clausius engine, you can use that and a Carnot cycle to build yourself an anti-Kelvin-Planck engine. A failure of the Clausius statement implies a failure of the Kelvin-Planck statement as well. So now that we have shown that this implication cuts both ways, we are in a position to say that both of these statements are equivalent statements. Which one of them is the second law? Well, take your pick. Any one of them. In fact, you will see many other versions of the second law as we go along these lectures. And any one of them essentially would be a valid version of the second law. All the other versions, including these two, would actually follow from them.